Hi everyone. In the last video we talked about how to be able to estimate the area under a curve from a point A to a point B using either a left-hand sum or a right-hand sum. And if I could just kind of summarize, we basically said that if we want to approximate the area under a curve, we could look at different rectangles and add up the areas of those individual rectangles. And the way that we did that was by looking at delta x, which was the width of each rectangle, and then multiplying by the sum of a bunch of different output values. So we called it something like f of x1 plus f of x2 plus so on and so forth. And it kind of, how many x's you have kind of depends on how many rectangles you want. So if you want 50 rectangles, you'd actually add up 50 things inside of the parentheses. And so just to write it in a little bit of a better way, let me write it like this. You can take delta x times, if you remember this notation, this summation from wherever I equals 1, like wherever you want to start as a first x value, and go up to n. N is how many rectangles do you want? And basically this is saying take f of xi. Now this notation is a little bit more advanced notation, but I hope you've seen this summation notation before. Basically it just says add up a bunch of the f of xi's, and the question is, well, how many xi's do you have? And well, that kind of comes from n saying how many rectangles do you want. So you're going to add up however many rectangles you have and then multiply by delta x out in front. Okay, and so in this section we're actually going to look at some new notation and another way to express this. Instead of talking about the approximate area under the curve, what we're going to do is we're going to actually let n get bigger and bigger and bigger and bigger. In other words, let n go to infinity. And if n goes to infinity and gets bigger and bigger and bigger, then what's actually going to happen is we're not going to just be talking about the approximate area under the curve. We'll actually be finding the exact area under the curve. So let's take our area under the curve, and we're just going to modify the formula that we had there just a little bit. The area, say the area under the curve from a point A, or x equals A, from A to B is what I'll say. So in other words, on the interval from A to B, instead of talking about the approximate area and saying let's get kind of as close as we can, if we throw a limit in there, we're going to talk about not just n being 10 or 20 or 50 or 100, but what if we take the limit as n goes to infinity, and you have basically thinking about infinitely many rectangles. Now, I will say this is a really weird idea because it's a weird idea to have infinitely many rectangles, because then their width is infinitesimally small. Okay, that's a hard thing to visualize, but basically the width gets smaller and smaller and smaller. There become more and more and more of them, and then those rectangles, if you will, that are there basically give you the exact values. On the curve, you actually don't just have an approximate area of the curve, you get an exact area. So here's the formula we're going to have. I'm going to write it like this. I'm going to say the limit as n goes to infinity of the sum of just what we had before, I guess, from I equals 1 up to n of f of xi. And remember, this is talking about the height of the rectangles. And then we still need to multiply by delta x. Okay, so this is going to say take, and remember we had been putting that delta x out front, but you could say delta x times each individual f value, and you just have delta x written a whole bunch of times. So really, I could put parentheses there. It's not needed because remember you're supposed to multiply before you add, order of operations. But we could just leave it where the delta x in this case is on the inside of the parentheses there. And it doesn't really change anything for us. So instead of writing the area under the curve every time, or the area under the curve from A to B, we're going to have a little bit of new notation for us here. So this is going to, let me give myself a little bit of space here. The new symbol or the new notation to talk about the area under the curve from A to B, and again, not the approximate area, but the exact area, is we're going to use this symbol right here. This is going to be a new symbol, new notation for us. It kind of looks like a capital, big, long capital S, kind of looks like a snake. And on the bottom, we're going to say from x equals A, where is your interval starting, to x equals B, where is your interval ending? And we're going to have this where this is, we're going to call this the integral, okay, integral of f of x dx. Now, we've seen a little bit of this before. We've seen some of this notation, and again, this means the same thing as what I had on the last page that says the limit as n goes to infinity of the sum from I equals 1 up to n of f of x to the I, not to 0, f of x to the I, or f of x subscript I should say. So f of x subscript I times delta x. And some things in this should look familiar. If you remember, you should remember seeing this dx notation before. You should remember that from when we talked about differentials. And do you remember when we talked about differentials and we found dy all by itself? When we get dy all by itself, you should get something with a dx in there. And this is still talking about, this dx is still talking about delta x. That is still the width. So another way to think about it is like the f of x is here. This big snake-looking thing, this big integral symbol right here, is basically a fancy way to say add up infinitely many things, add up a bunch of things. It's a big way to kind of add a bunch of things together. And so this kind of says add up all of the f of x, which is like your heights of the rectangles, times your delta x's. Let me erase this. This comes from, we've seen that before from differentials, but f of x is your height, where dx is your delta x. That's kind of your base of each rectangle, or the width of each rectangle. So this is basically saying add up all of your height times bases. Okay, but this is some new notation that we're going to see. And when you see this symbol, the integral here, I want you to think every time area under the curve. Okay, area under the curve. We're going to see in a minute. It's a little bit more detailed than that. But area, basically, when I say under the curve, what we're really going to be thinking about is the area between the curve and the x-axis. Okay, let's say you have a curve down here, and earlier I drew ones that were only positive, only above the x-axis, but this one's below the x-axis in certain places. When I say the area below the curve, I don't mean the area down here. That's not what I'm talking about. What I mean is the area between the curve and the x-axis. So let's say, for example, here, you're talking about over here from maybe -3 up to 5, the area under the curve would technically be this area right here that's shaded, and then also include this area right here that's shaded, because really when I use the phrase area under the curve, probably a better way to say it is the area between the curve and the x-axis. Now this brings up a really interesting point, is that sometimes when you're talking about the area under the curve, or what we really mean is the area between the curve and the x-axis, if you have a part of a graph that is above the x-axis, like we had in our previous video, and we're just looking at this area right here, it makes sense that that area would be considered a positive value, a positive area. When we talk about the integral from A to B of this function, it makes sense that the integral is going to give you some kind of a positive value. But let's say we have a different function. I'm going to look at a function down here. What if we have a function that's, I don't know, from A to B is pretty much strictly down below the x-axis? So we're really looking at this area right here. Now this is a little tricky because when we say area, we typically mean, and we tend to think positive. It's got to be a positive area. And technically that's true. When we talk about area, the definition of area is that it's a positive value. But if you remember back in pre-calculus, there were times when we talked about polar coordinates, where you had a radius length, and sometimes that radius length could be negative. Or when we talked about speeds, sometimes we could talk about what we meant if we had a negative speed. Now, can you technically have a negative speed? Not really. The negative there really just talks about which direction your speed is going in, or which direction you're moving in. And same thing with a negative radius back in pre-calculus. The negative doesn't really mean that you can have a negative radius, because radius is technically a distance. But when we had a negative radius with polar coordinates, like you could have r comma theta being -5 comma 30 degrees. And we could talk about what that means. And the negative for the radius just means go in the opposite direction. So the negative kind of tells us about the direction of things, and that's true in this case with integrals as well. If you look at this function, and this is just some random function that I've drawn that is below the x-axis, technically the area between the curve and the x-axis, or we would say the area under the curve here, is technically a negative value, not because it's a negative area, you can't really have a negative area, but because that area falls below the x-axis. So if you're looking at the integral from a to b of f of x dx here in this situation, remember that the f of x dx is talking about the width times the height, or the base times the height, you might say. And if you look at drawing rectangles in there, the base, or the width of those rectangles, is going to be a positive width. But if you use the function value, if you say delta x times f of x subscript I, when you have a value below the x-axis, the f of x subscript I down here is actually going to be a negative value. And so you're going to have a whole bunch of negative values that you're adding up. It should make sense, or it seems to make sense, at least in this case, that we have an integral from a to b is actually going to give us a negative value. And the fact that we get a negative value is strange. It's weird to us because it means we get negative areas sometimes when we're talking about the area under a curve, when we're talking about integrals. So that brings up an interesting question. What if you have a function like this? What if you have a function that's partly above the x-axis and partly below the x-axis? What do you think is going to happen? In this case, I've kind of intentionally drawn it so it looks like the area above the x-axis has a pretty equal or similar area to what's below the x-axis. And so in this case, if the area above the x-axis, as in like this part right here, and the area below the x-axis right there, if those are exactly the same areas, it's actually possible to have an integral from a to b. So if this is a over here and this is b over here, to have the integral from a to b of f of x dx actually being equal to 0, because you have some positive area. And I tell you what, I'm going to put positive area here. I'm going to put the positive kind of in quotes, because we typically think about area as positive, but down here, the part underneath the x-axis, technically, we kind of think about that as negative area. And again, I'm going to put negative in quotes there, because area technically shouldn't be negative, but the fact that it's below the x-axis means that we're going to get negative function values there. And so when we use the formula that we saw on the first slide about the formula for the area under the curve using this integral notation, it uses this f of xi. Those are going to be negative values. And so we're going to actually end up getting a negative value for the integral, even though it seems like we're talking about an area. This tends to trip a lot of people up, but I want you to think about kind of, is your area above the x-axis or is your area below the x-axis? By the way, oftentimes we talk about a here as being the lower limit, and b we often talk about as being the upper limit. Some of the vocab of this kind of stuff you'll get along the way as we deal with some examples, but the lower limit and the upper limit of integration are technically a to b to say where are you starting your interval, where are you ending your interval. Okay, I hope you've enjoyed this video. There's going to be another one to come with some examples.